fun new game. Coughing. All right. How's everybody's break?
Not as exciting as yours.
Yeah. Yeah.
I want to hear about it.
I had a good break. Yeah, I went to Vegas. Yeah, it was fun. Went to the Pink concert on last Sunday. That was fun. In Nashville. Yeah.
Going next
It's
month.
only the 9th time I've seen Pink in concert. So. Yeah, it was 8 or 9. One or two. When you lose count, you don't see it in concert times. But
She do the same thing as always? Or no?
yeah. Well, it's ridiculously amazing what she can do. She sings while, doing all sorts of acrobatic crap. It's stupid. That's what it is. But yeah, it was fun. And I went to Vegas. I was supposed to watch some basketball in Vegas because there were a lot of the conference tournaments were going on. So I saw the women's championship games while I was there. It was fun. It was a lot of fun. Had a good time. Didn't win any money, but it was a good time.
Did you lose money?
Oh, yeah. But I mean, you have to keep the lights on out there, so. Oh, goodness. All right. Anyway, any questions before we get started? All right. So today we're going to talk about another analysis of variance, which is referred to as two-factor analysis of variance. Maybe. Come on, erase. There we go. We're actually going to have two different cases for this two-factor ANOVA. So remember last time with the one-factor ANOVA, we were trying to determine whether or not a group of means were all the same or if there was one that was at least one that was different. That was the one-factor ANOVA, right? So what we're going to talk about in this particular scenario is we have a bunch of different classifications, a bunch of different attributes that we might be trying to compare with each other. So, for example, maybe you are looking at different hybrids of a crop and its yields in different climates. So maybe you've got 3 different hybrids of crop and you've got 3 different hybrids, or excuse me, 3 different climates that you're trying it out in and seeing if there's any difference or if there's any variability, if you will, in the yield rates, depending on hybrid and depending on where it's located. Okay. So to that end, what we're going to have are basically cells of ideas. So say you've got attributes 1, 2, 3, and so on going this way. I'm not going to write out a whole bunch of different things. We're going to talk more about specific examples as we go through problems. Say you had 1, 2, 3 going that way. Maybe we had 1, 2, 3, 4 going this way. So we can imagine these being as cells, right? You can think about it as like an Excel sheet, if you will. So in the first case, we're going to have one observation per cell, essentially. In the next case, where we're going to talk about possible interaction between cells, we'll have multiple observations in each cell. So right now, we're just going to have one observation in each cell. We're not going to worry about interaction between the cells. All right? So in each of these, we can calculate an overall mean. Right? We can certainly take all 12, the way I have it written is 12, right? I can certainly take all of these things and have an overall mean, right? We agree with that? Okay. So if we did an overall mean, again, let's say I put that down here in this lower right-hand corner, and I'll call it grand mean again. That would be kind of our x. We used that double dot notation last time, remember? Right? So that's just that's the mean of everything in our sample. Right? But we also have, we could also do means here in each individual row and each individual column, right? So we would have a mean over here. This would be row 1, and then across the column, so we use the dot on that, right? So that would be our x1 dot. Oops, I put that grand mean in the wrong spot. Need to be down a spot here, sorry. All right, so we would have an x2 dot and x3 dot going across the rows, right? This is much like what we had to set up the last time, right? Over here, we would have an x bar dot 1, x bar dot 2, x bar dot 3, x bar dot 4. And then, of course, in each of these, we would have, I'm not going to write them all in, but say here we would have an x sub 2, 3, right? That's how we did our ij. Sound familiar? Oh, I'm just doing it. We could do this for an arbitrary long, arbitrary many rows, arbitrary many columns. I just wanted to do a smaller example to see what we're doing. All right. So here's the idea. There's going to be some difference between each of these row means and the overall. Well, there probably will be a difference between the row means and the overall mean, right? There will probably be a difference between each of these column means and the overall means, right? What we're going to do is we're going to make an assumption that there is an overall effect for the rows and the columns that works in some sort of an additive way. What we mean by that is that in the ij cell, there is a mean, the mu sub ij. So this, again, this mu sub ij is the mean for the ij cell. So if I were doing this 2, 3 entry again, the mu would be 2, 3. So we're referring to the mean here on the 2, 3 spot. Okay. That mean there should be equal to the mean, the overall mean, the mu, and then plus some row effect, which we'll refer to as alpha, and some column effect, which we'll refer to as beta. We're making an assumption that there's an additive way to do this. Okay? So this alphas are your row effect. Your betas are your column effect. So to illustrate what we mean by these row and column effects, let's look at a specific example. Let's look at number 2 on page 397. And I think this is one of, no, it's not, never mind. I was going to say something and I realized I was going to say something wrong. All right, so this is 7.6-2. These are the entries in the cells. Notice that was why I did 3 and 4, because that was the first problem that I was going to talk about. I had 3 and 4. All right. So the first thing I'm going to compute here are the different means. Okay? So these along the bottom here, these 4 will be your column means. These 3 will be your row means. And we'll put the grand mean down here. All right. The column means are pretty easy to do. That's 8. This one is 5. This one is 9. This one is 10. They made the data spread out nicely so you can do it pretty quickly. Across the rows, what 15 and 9 is 24 divided by 4 gives us 6. 22 and 18 is 40 divided by 4 is 10. And 18 and 14 is 32 divided by 4 is 8. So you get 8 for that. And if I remember correctly, I believe your overall mean, the grand mean, is also 8 here. We can check it, but I'm pretty sure it's 8, if I remember doing it correctly from last night. Doesn't matter. It is what it is. It illustrates the rest of what we wanted to do. Okay. Anyway. So what this problem asks us to do, these are, the values that are up here are your mu sub ij's. Okay? So if these are your mu sub ij's that are in the array, it's asking us to figure out what the row effect and the column effect is on that particular cell. Okay? So up here, the 6 has to equal, that's our mu sub ij, the 6 is, has to equal the mu, which is 8. That's our grand mean, right? Okay? Now, of course, 6 doesn't equal 8, so there must be some effect from the row and some effect from the column. So how do we figure out what those are? Well, let's look at the rows and the columns. Here's my row, right? If I'm in row 1, I'm in a row with a mean of 6. How far away is the 6 from the grand mean? 2. It's 2 below, right? So the row effect in this case is going to be a -2. That's our, since we're up in the row, that we're in the 1, 1 spot, this is alpha 1. This is mu sub 1, 1 here. Does that make sense? Then look at our column. We're in column 1. The mean of that column is 8. The overall mean is also 8. So what's the column effect here? 0. There isn't any, right? So that would be your beta 1. Does that make sense? And in fact, you can figure out your alphas and your betas pretty easily, right? This is row 2. What's your alpha 2 going to be? 2, and our alpha 3 will be 0. Beta 2 will be -3 because it's below, right? Beta 3 will be 1, and beta 4 will be 2, right? And then we can check that these work at any given point. So let's say we did the 2, 3 entry here. If we did mu sub 2, 3, that's 11, right? The grand mean again is 8. The overall mean is 8. What did we say the row effect was for that row? 2. And the column effect was 1. Right? That was our alpha 2 and our beta 3. And does that equation work? Yeah. Does that make sense? So that's where the row and the column effects are coming in. Now again, it should make sense, the way that we're doing these, that if you add all of your row effects together, you better get 0, right? Because some of the means should be below, some of the means should be above. If we're doing this in an additive fashion, when you add all of your row effects together, you better get 0. When you add all of your column effects together, you better get 0. Right? Does it make sense? We better get 0 in each of those cases? Because the mean of each of those should be the mean of the grand mean. Okay. All right. So what we want to test is whether or not there's actually any row effects at all. So the testing that we're going to be doing, we actually are going to have 2 alternative hypotheses plus, 2 null hypotheses plus an alternative hypothesis. So we'll have an H sub A, The A's we usually refer to them as the rows. So your H sub A is that your row effects are all 0. What do they use for the letter? Oh, they just use an A. They do use an A. So the little a is the number of rows. Your null hypothesis for the betas, for your columns, looks similar. So really, we've got we're going to be doing two hypothesis tests at once. So you're going to be the null hypothesis that there's no row effect will be tested against there's at least one row effect, and the null hypothesis of that there is no column effect is that there's at least one column effect. Okay. All right. So we have to have somewhat measurement of how we're going to do this. And I just want to illustrate where the measurement comes from, but we're going to use Excel to get the results. Okay? We're not going to do these by hand because that's crazy when we have technology to be able to do this. Why do it by hand? But we do want to understand where the statistic is coming from. I don't want to just tell you, read the table, and then not have any understanding of what the hell the tables even mean. Okay? So let's talk about this again. So we can do a total sum of squared errors, like we did with the ANOVA, the one-factor ANOVA, right? The one-way ANOVA. So to that end, when we do this, we can do a total sum of squares, which again, if we think about just the way it's set up, that means each of these x sub ij's will subtract from our x bar double dot, right? And square it. Okay, so this will be the double sum. We'll have I goes from 1 to A, and J goes from 1 to B. And we'll have our x sub ij minus our x bar double dot squared. Okay? We already know that if I take this, divide it by sigma squared, and multiply it by its degrees of freedom, I get a chi-squared random variable, right? We've already talked about that before, because that's sample variance, right? So if I take this and multiply it by a times b minus 1, because that would be the total number of entries minus 1, that'd be the degrees of freedom, right? And divide it by sigma squared, I have a chi-squared random variable, right? We talked about doing this in the last section. It's the same kind of stuff, right? So this is chi-squared with ab minus 1 degrees of freedom. A times b minus 1 degrees of freedom, right? Okay. Now we're going to do the same kind of trick that we did last time. We're going to add and subtract some things in here and regroup some things. This is on page, sorry, go ahead.
You said it's a times b minus 1?
Yeah, a times b minus 1, yep. We're going to regroup some things, add and subtract some things, much like what we did before. So this is on page 391 if you want to see where it's located. So I want to add and subtract an xi bar dot, or x bar sub I dot. And I'm going to add and subtract an x bar double dot. And an x bar dot j. And rearrange it. I just want to make sure, I'm looking at the book because I want to make sure I get all these in the right spot. All right, cool. Shoo. All right, just to see, make sure that everything here is equal. Added and subtracted x bar sub I dot. Added and subtracted x bar sub dot j, added and subtracted x bar double dot. So it really is the same thing. Okay? Now, why did we do this in this fashion? Well, what is this? Well, this is the difference of these means against the grand mean, right? Right? This is the difference of these means against the grand means. And then we're going to look at this part at the end here. Now, much like what we did last time, we need to square this thing out, which is ugly because I've got to square basically a trinomial here, right? But what happens is, and you can go through and check it, which we're not going to do here because it's just an exercise in algebra. What happens is that all of your inner terms, when you do all the distributing, they all cancel. They all go to 0. Just like they did in the last, remember when we squared out the middle and the middle term went away the last time? Same exact thing happens here. So when you square this out, all you get is the following. You'll get a b times the sum from I equals 1 to a of x bar I dot minus x bar double dot. And squared. The reason for this, where the b comes from, when I square this term, there's no j's, right? So this inner sum here, I'm just adding this to itself b times. That's where this b is coming from. Okay? The next one is an a times the sum from j equals 1 to b of x bar dot j minus x bar double dot squared. Again, that's this one. There's no i's, right? Right? So if I think about just flipping the sum around, I'm going to add that to itself a times. That's where that a is coming from. Okay? And then the last one is still a double sum. I equals 1 to a, j equals 1 to b, x sub I j minus x bar I dot minus x bar dot j plus x bar. I hate these dots. This looks like what you would like to have had happen in algebra class, but you know that you actually have to do distribution. It works nicely here because all those middle terms will cancel if you actually square it out. Okay? All right. Let's analyze each piece now. This looks a heck of a lot like was in the previous section, right? When we had the n sub I minus 1 pieces, all those n sub I things, right? In the previous section, we had things that looked like these, didn't they? And these were chi-square, right? This is a chi-squared random variable, which has, if I divide it by sigma squared, it's a chi-squared random variable. So this one has, what, a minus 1 degrees of freedom. Okay? It's this exact same argument as what we did in the previous section, by the way. This right here is going to be a chi-squared random variable with a minus 1 degrees of freedom. That looked like, in the previous section, that was our sum of squares between treatments. Yeah, it's the sum of squares among the different treatments. It was the SST. Okay, that was our SST for one of them. So this it's chi-squared on a minus 1 degrees of freedom for the exact same reason it was in the previous section. Okay. All right. So where am I going with this? This is chi-squared. This one's also chi-squared. Same reasoning. It's on b minus 1 degrees of freedom. Same reasoning as what we talked about in the last section. All right. Let's go through this. Overall, this was chi-squared, right? As long as we divide everything by sigma squared, I should say, right? This is chi-squared, this is chi-squared, this is chi-squared, so what does this one have to be? chi-squared, right? That was the theorem we talked about last, I mean, it's been a week and a half, but we talked about that theorem, right? So this also turns out to be chi-squared. Okay? Look at the form of this thing. We said that we were assuming that we had some sort of an additive model for this, right? The mu sub ij was equal to mu, right? Mu minus is mu plus the row effect plus the column effect, right? Well, let's look at this piece right here. I can rewrite that piece, and I'm just going to rewrite it underneath it. I can rewrite this as x sub ij minus x bar sub I dot minus x bar double dot minus x bar dot j minus x bar double dot. Oops. I did do a triple dot, didn't I? I can't get it to erase. And then minus x bar double dot. I'm just looking at what's inside the parentheses. I'm not going to write all this squared again. Okay. Now, why did I do this? Let's think about it in terms of the model. The model was mu sub ij is equal to mu plus alpha I plus beta j, right? Grand mean plus row effect plus column effect should be the mean for the cell, right? Here's your cell, right? If I subtract grand mean, row effect, and column effect, we should get 0, right? We agree? If there's no effect, but in particular, it doesn't matter if there's an effect or not. If the model is accurate, if it's additive, this has the exact same distribution no matter what, whether or not the null hypothesis is true. Because we've got it written as cell minus row effect minus column effect minus overall mean. Okay, so no matter what, this last term should have the exact same distribution no matter what's going on. Okay, so to write down the different pieces now, this first piece, this will be our SSA. That's the sum of the squares for the rows. The second piece will be our SSB. That'll be the sum of the columns. And then finally, the last piece will be our SSE, the sum of the squared error. But it's that sum of the square error that we're going to use as kind of a measuring device. Because whether or not the null hypothesis is true, that always has the same distribution. Because it's not based on whether or not the null hypothesis is true. It's literally based on row effect, column effect, overall mean. Right? So regardless of whether or not the null hypothesis is true, has no effect on the distribution of the SSE. Because it's written in terms of what the model assumption is. Okay? It's the other two that depend on whether or not the null hypothesis is true. Okay? So, our test then will be an F test. Because we want to test what the size of the SSA is relative to the size of the SSE. That'll test the null hypothesis for the A. This will tell, and then the same idea here, relative size. So we'll do the relative size by doing the division of two chi-squared random variables, right? When we do the division of two chi-squared random variables, we get an F test, F variable. So we'll do an F test on this. Okay. All right, so as far as degrees of freedom go, we said that this one is A, B minus 1 for your degrees of freedom, right? This one was A minus 1. This one's B minus 1. If you do the algebra, this one has to be A minus 1 times B minus 1 to get it all to work out right. So again, these are the degrees of freedom. Remember it's the same argument we had before. Each individual piece is chi-squared except for the last one. So it also has to be chi-squared if it fits that quadratic form idea that was the theorem. Right? And then the degrees of freedom have to match when you add them up. So if you do the algebra, that last degree of freedom has to be a minus 1 times b minus 1. All right. So then our F test will be our F statistic to test your HA. You'll use F is equal to SSA over A minus 1 over SSE over A minus 1 times B minus 1. And then to test your H sub B, it's the same statistic. You're just going to replace the top. Oops. Okay. And then if you're using a table, you would pick a significance level. You'd go look up the critical value. And if your F is bigger than the critical value, your F statistic is bigger than your critical value, you would conclude that there is a row effect or there is a column effect, depending on which one you were looking at to start with. All right, so let's do that. Like I said, I just want you to know where it comes from. All right, we're not going to do this calculating it in this fashion, but I want you to understand at least some idea of what's going on behind the scenes. Okay, we're doing sums of squared errors essentially, right? So we've got chi-square random variables. One of the chi-square random variables is only based on the assumption we're making for the model, not the actual values of whether or not the null hypothesis is true. So we're using that to measure the relative size of that versus the other two, and then making a conclusion based on if that ratio is too big. If the ratio, because this ratio should be small if the null hypothesis is true, right? If there's no row effect, these two things should be close to each other, or no column effect, depending on which one you're looking at. All right. So let's see if we can look at this. So let's just look at 7.6-3. This is one of the data. This is one of the data that I sent you. So here's how this works. I put the labels in here because it was the way it was labeled in the book. Turns out, what we're going to do here first, we're assuming that there isn't any interaction between the cells. Later on, if we have interaction, we have to do something. We have to do a different test. Okay. So I mean, it's still ANOVA, but it's just the test looks a little bit different. All right. So let's see how we do this one. All right. So there it is. Got a cursor finally. All right. So under the data analysis, there's two different two-factor ANOVAs, with replication and without. Right now we're going to do the without replication. What the without replication means is that we're assuming that there's no interaction between the cells. Okay? So in this particular problem, in your 7.6-3, they're talking about different strengths of concrete cylinders that they did with different treatments in different batches. And basically, they said to assume that there's no interaction. What I said in the problem. All right. So no interaction means we're going to do ANOVA two-factor without replication. And it's actually easy to use. Input range, we're just going to grab the data without the labels. When we do two-factor with replication, guess what? We get to grab the labels too. That took me about a half an hour to figure out that I had to have labels on my things to get it to work right.
How do you do the analysis in
Did you import the
No.
tool pack?
That's what I mean.
Okay.
I think it was under tools.
Under tools.
Cell add-in.
Yeah, tools and then Excel add-ins. There it is. Analysis toolpack.
Okay.
Yes, there it is.
Okay.
Ta-da!
Thanks.
Yep. I don't have a Mac, so
Well,
thanks,
like the
Sid.
Two-factor with repetition?
Without.
Without.
Yeah, we went without in this case. Okay. All right, so this one, again, pretty easy to use. Just grab the data. Don't grab the headers. Okay, just grab the data. Alpha level 0.05, unless I tell you if something different. Most of them are all 0.05 anyway. Let's define an output range. I just clicked on output range. If you don't do that, it'll just open it up a new worksheet and put it in there. I'd rather just see it. And just click on a cell where you want it. Or you can type it in too. It doesn't really matter. And then I'm going to hit OK. And a whole bunch of stuff's going to pop out. All right. So let's just talk about the different things that are going on here. The first part is just giving you a summary of what's going on in different rows and different columns. So here is your different row means for these first three here. So those would be your X bars and I dots. Okay. These parts here will be your X bars of dot J. Those are your column means. They also give you the variances in each of those as well. Okay. That's not really the important part for our purposes because we want to know what the result of the test was, right? This is just giving you those summary statistics for those things. All right, so down here is our actual analysis of variance. All right, so this row, this is your SSA, the 89.2 in this one, that's SSA. Your 363.6 is your SSB. And the 46.8 is your SSE. Notice here you can check your degrees of freedom. There were 3 rows, so the row degree of freedom is 2. There were 5 columns. Your column degree of freedom was 4. Your degree of freedom then on SSE is the product of those two. So that's why we get 8 there. So if you were looking up numbers in the table, you would need those, right? The MS is your mean square error. Remember, your mean square error is taking your sum of square error and dividing it by the degrees of freedom. So the MS column is just the SS column divided by the DF column. Okay, that's all this is. Should be, yeah. Yep. If you can check the numbers real quick. All right, so then your F statistics here again. This F should be your mean square error for the rows divided by your sum of squared error, your mean square error for overall. Okay. So if you take the 44.6 and divide it by 5.85, you should get that F value. If you take the 90.9 divided by the 5.85, you should get that value. Does that make sense? Okay. These F values have really low P values, right? These P values are both under 0.05, which means you would do what? Reject or not reject? P values below 0.05, you reject, right? Also, notice that it gives you the critical values for your F, right? Your F is bigger. Your F statistics bigger than the F critical value, so it also tells you that you reject. Notice it's reject in both cases, right? So the rejection means that there is a row effect and there is a column effect. So what would it mean in this context is that the treatment mattered, whatever treatment they're using to treat the concrete mattered, and whatever batch they did was also mattered. But there is a row effect and there is a column effect. Does that make sense? That's the idea. All right. Questions on that at all? Did you get it to work?
No.
No?
I think I just forgot it. I just added it in.
Oh, you just did. Okay. So let's just go to the. It is. Okay. Put that on there. There it is. Okay. There we go.
I don't know why I didn't mark
That was
it.
weird. That was weird. All right. So, in this particular case, it said assume that there is no interaction. So, if we wanted to go to another problem, which is look at the 7.6-5. In the 7.6-5, there's the context is that there was a psychology student was testing food consumptions by rats, whether or not it would be affected by a particular drug. So some rats were given drug, some rats were given placebos, but there was also differences in the rats between being male or female and whether or not they were sterilized. So that's why there's 4 different categories for the different types of rats. So we've got non-sterilized male rat, sterilized male rat, non-sterilized female rat, sterilized female rat. Okay. All right. So in that case, of course, there could be some interaction that's going on between, well, depending on, did a drug affect a male versus female differently? Did a drug affect the castration versus the, whatever the other one, the sterilized male and the sterilized female one differently? There could be interactions. The example they give in the book probably explains that a little bit better. They're talking about different types of gasoline with different types of cars. And it might be the case that a particular car performed better or a particular gasoline performed better, but if you put the wrong gas in the wrong car, there might be a bad interaction. Okay? So, same idea with drugs. One drug might work well with a certain type of person, another drug might work well with another type of person, but if you mix the 2 drugs, it wouldn't necessarily work well. Okay? So those are the kinds of interactions that we're looking for. All right. So when we do this with interaction, we assume, just like what we did before, we assume we have an additive model. And I'm not going to go through all of the gory details like we just did with the previous model. It's the same idea, right? We assume we have an additive model where the individual cells are based on the overall mean, a row effect, a column effect, and an interaction factor. So there's an extra factor on the end that you use the gamma sub ij in the book to represent that. Okay? So you've got also an overall interaction factor that pops up that might affect what's going on in a particular cell. So if you went through all the gory details, you can break it all apart again. You get a sum of squares for your row, a sum of squares for your column, a sum of squares for your interaction, and a sum of squared error. Again, if the model is accurate, your sum of squared error doesn't depend on whether or not the null hypotheses are true. So you use that as your denominator and measure from that, just like we did before. And then we have 3 separate null hypotheses to test. There's no row effect, there's no column effect, and there's no interaction. Okay. We're going to do all of that with an ANOVA, but we're going to do the with replication in this case instead of the without replication. So going into the data analysis again. In this case, I want with replication. All right, this one, I have the labels typed in. When you're doing the ANOVA without replication, you don't want the labels. When you do the ANOVA with the replication, you do want the labels. Okay. So when we do the input range, I need not only to grab the data, but I also need to grab the labels. So I'm going to put the MCFO in my range and my drug and placebo in my range. Okay. And then there's one more thing we have to worry about. It says rows per sample. So notice when we're testing for interaction, basically we're going to do multiple things in each of these treatments here. Okay? So when it says rows per sample, we've got 5 rows in the drug and 5 rows in the placebo. So we got 5 in each sample here. Or rows per sample is 5.
Well, it must be the same amount.
Yeah, it needs to be the same amount. Yep. You know, all of these things have to be evenly distributed for this to work. And then the same idea, pick your output range to be wherever you want it to be, and hit OK. And then again, a whole bunch of stuff comes out. The top part again is just summaries, doing a row summary and a column summary. Well, it's a row per column summary, I guess I should say. And then, if we go to the bottoms where your actual ANOVA is done. All right, so, pardon me. Your row degrees of freedom here is just 1 because there were 2 categories, right? Your column degrees of freedom was 3 because there were 3 categories across. Your interaction one is, for that one, you take, what is it you take here? You take the AB. Your A is the number of rows, your B is the number of columns. So your A times your B, and then you multiply it by C, which is the total number of cells, minus 1. Or, that can't be total number of cells minus 1. It's total number of, oh yeah, no it's not. It's, check the C again, sorry. Oh, it's the number of observations per cell. So there was 5 observations that were taken per cell. So it would be, why is that only 3 then? The numbers are right. Why is it only 3 degrees of freedom? It seems like there should be more. A times 1. No, anyway, come back to that. We'll spend time. Should have paid a little bit more attention when I was reading it last night. Sorry. I was trying to make sure I got all this stuff to work. Anyway, this is your interaction degrees of freedom. Still not sure why it's 3. This is, of course, is your leftover degrees of freedom. Making sure everything adds up, right? You've got 35 and 4 is 39. There were 40 total entries, so there should be 1 less than the total number of entries. Okay. Mean square again is just taking your sum of squares divided by degrees of freedom, because we're taking those chi-squared random variables again and dividing by degrees of freedom, and then doing a ratio. That's how we're getting our F statistics. Okay. Here are your p-values. So this is your p-value associated with the rows. Is there a row effect? Does it look like there's a row effect based on that p-value? Would we reject or not reject based on that p-value? Reject. So does it appear there's a row effect? That there's a difference between drug and placebo, essentially? It does appear, right? Because it's less than 0.05 for the p-value. We reject it, so it appears there's a row effect. Does it appear there's a column effect? You know, 3.44 times 10 to the negative 9th. Yeah, that's pretty small p-value, right? So we would reject, right? So it appears that there is a column effect, so there is some sort of a drug effect. The drug effect matters whether or not you're male or female or sterilized or not sterilized. Okay. The last one, the interaction. The interaction says, is there interaction between things? What we mean is that is there a difference between drug in female versus drug in male, or placebo in male, placebo female, and those kinds of things. Well, looking at this, do we reject with that p-value, or with that F statistic being less than the 2.9? Do we reject in that case? No. So is there any evidence for interaction here? No. Okay, so we would say there's no interaction here. No, there's not evidence for interaction, or at least there's not enough evidence for interaction. We'll do a couple more of these examples on Wednesday. Make sure that we're all on the same page with this. Okay. Again, like I said, I'm more interested, of course, in being able to do the tables, or have Excel run the tables for you, and being able to interpret it. But you also should understand where these statistics are coming from. Okay. So that's why I went through the first part a little bit more in detail than the second part. So we'll do more of this on Wednesday. Have a good one. I should have your coffee-stained homeworks back to you then, too.
We have a test next week.
Is it next week?
Yeah.
Good. I didn't want it to be this week.
No, it's not this week.
Okay.